Okay, so we had a lot of preliminaries. Now let's get to the point. What we want to do is localization. So, as I said, the idea is to reduce the full path integral to a finite dimensional integral. This is. So, we need to choose a supersymmetry. So we had up there before different supersymmetries acting on our fields, but we will choose a transformation delta of the fields. So it's some supercharge. It's a fermionic transformation. I'll specify in a bit what that is. And we will require that delta squared is a bosonic symmetry. In the case of S3, it will be a rotation around S3. And then define the partition function and the function of t to be the integral, the path integral over all your fields, e to the minus s minus t times delta v, where v is a fermionic quantity. And so far I haven't told you what it is. It's up to me to choose it. So now we can calculate what is the derivative of z with respect to t. This will just break down a delta v. So this is equal, now I have delta, I can write it as delta of the v e to the minus s minus t dot delta v. And then I need to correct the things that I missed, plus v delta s e to the minus s minus t delta v plus v t delta square v e to the minus s minus v t delta. Okay, so now we have three terms, but we assume that delta is a symmetry. So delta of s is equal to 0 because it's a SUSY. Delta square of v is equal to this symmetry, bosonic symmetry, acting on v, and we're going to assume that this is also equal to 0. We require this. So when we choose v, we're going to have to make sure that it will satisfy this. When we choose v and delta, we need to require this. And then we have delta of the whole thing. So this is an integral of a variation. So you want to consider this as a total derivative and say that this is equal to 0. And there are two reasons to worry about this. First, you need to make sure that this symmetry is not anomalous. So the measure is also invariant under this supersymmetry. So delta is not anomalous. then there is the other thing is that you need to worry that in field space there is no boundary term in this integration, in this total integration. And so that's a little bit subtle, but usually you assume that the fields decay and so on, and that this will not be a problem. So for the most part, everybody ignores this issue and just hopes for the best. So assuming you did that, that tells you that dz dt is equal to 0. So your partition function, z, which is equal to 0, is also equal to the limit of t going to infinity of t. And this is what we're going to calculate, because when t goes to infinity, we have in the path integral e to the minus t times delta v. So if delta v is greater or equal to 0, you can you will have there e to the minus t delta v is dominated by the solutions of delta v equals 0. And this is the equation we need to solve. And if we are lucky, there is a finite space So what I described here is a very, very, very general procedure, but there were many, many ifs along the way. So you need to make sure that all these ifs are satisfied. Delta needs to be fermionic, V has to be fermionic, delta cannot be anomalous, delta has to square to a symmetry, and V has to be invariant under the symmetry, V has to be positive semi-definite, and if this is going to be useful, the space of solution of delta V, the vanishing space, is very small. And if all this works, then we're in business. So of course this will work in the examples we have, but there isn't a general rule for when this is doable and when not. So this is the general field. So then, okay, we have a finite space of solutions, and this is which dominates the action, and then we can actually proceed and do explicit calculations. I will explain them in the particular example, how one proceeds beyond this point. Any questions about the general procedure? So I mean, I will do it explicitly for the case of these 3D supersymmetric fields. So let me be explicit in 3D. I will take the metric to be r squared over 4 theta squared plus sin squared theta phi squared plus cosine theta. So this is the metric on S3 written in the hop fiber form. So you have here an S2 and over it a circle vibration. And I promised you the symmetry, which will be a rotation, so actually delta squared, we will take it to be the translation along this U1. So any quantity that we're going to want to calculate using this as symmetry will necessarily have to be invariant under translation in the psi direction. So you can calculate, for example, an expectation value of a Wilson loop, as long as the Wilson loop will be extended along this circle. You can calculate two Wilson loops. Each of them has to be along these two circles in the psi direction, but they can be at two different values of theta and phi. You can take two circles which are, that's known as half-linked circles. You can calculate any number of Wilson loops linked in this way by this calculation. You can consider in principle, this hasn't been done, but you can consider in principle a surface, a two-dimensional object, which is spanned by this direction psi, and any submanifold of this, any other curve on this S2, that in principle could be supersymmetric. One has to check that it is indeed supersymmetric, but then if it is, then localization could work for it. So I told you that epsilons, the supersymmetries are going to be killing spinors, so I wrote a metric. Now, to write down the killing spinors, I would need to write a I-bind and solve the killing spinor equations. I will actually not do that, but there are, in this metric, there is a killing spinor which is constant. So if you remember, I wrote in flat space the usual Poincare symmetry involve constant spinors, and the conformal symmetries involve space-dependent spinors. There is just a linear dependence in x in the coordinates in flat space. In this case, in this metric and the correct choice of a frame, there is also a constant killing spinor, so it's very easy to work with it. So what I will do is I will consider the variation delta with epsilon equals epsilon bar is constant spinor. So as I said, this is where the notation always is confusing, because I will use the same epsilon and epsilon bar as I had before for a generic killing spinor, but from now on I mean this particular killing spinor. And in particular, if you remember before I had these transformation, I had in delta D was equal to epsilon bar gamma mu epsilon d mu of d plus other terms. These other terms are actually zero, proportional to sigma. These were zero for killing spinors. Now, this vector is exactly going to be this thing. So this is equal to d psi of d. So everywhere I'm going to have, as I said, translation along the psi direction are going to be symmetries. So that's the first thing. Choose the delta. The delta will be made by both epsilon and epsilon bar transformation at the same time with the same proportional to the same constant spinor. And delta square is the good. Now I need to choose what V is. So for V, I'm going to take delta epsilon of 1/2 lambda bar lambda minus 2 d sigma. So this epsilon is that particular epsilon that I chose. So delta of V is equal to delta epsilon bar delta epsilon of this so this you need to calculate. What is this double variation of this simple quantity? But I will tell you what this is. Sorry, there's a trace. I will tell you what it is. You can check it as homework. This is equal to trace up to boundary terms to integration by parts. This is equal to 1/4 f mu nu because delta of lambda gives you f mu, for example, plus 1/2 d mu sigma plus 1/2 d plus sigma over r squared. This r is a constant, it's not a coordinate. R is the radius. Plus I over 2 lambda bar gamma mu lambda bar. Yes.
So, at some point you said that epsilon equals epsilon prime.
Yes. Delta epsilon is not equal to delta epsilon prime because I defined the variation with respect to epsilon as different to the variation with respect to epsilon prime. This is exactly where I said I'm going to be very confusing. Do you understand? So in the equations before, I wrote the variation delta of sigma is equal to epsilon bar lambda, I don't know, 1/2 minus lambda bar epsilon, something like that. Delta epsilon of sigma is equal minus 1/2 lambda bar. That is different from delta epsilon bar of sigma, even though epsilon and epsilon bar are going to be the same killing spin. It's really a bad choice of notation. But,
So delta epsilon square is...
delta epsilon squared is 0. Yes.
But delta epsilon bar, delta epsilon...
No. Delta epsilon bar is this a commutator. So the variation that I'm doing is delta epsilon plus delta epsilon bar.
But then...
This square is the anti-commutator.
But then if delta epsilon bar is a proper derivative.
This is the...
Why isn't delta D?
Because here I need to take the anti-commutator, and there it's not the anti-commutator. And really we should start using a clearer way of saying this. So I should use actually, I should use here a particular epsilon naught everywhere. So what I choose here is epsilon equals epsilon bar equals epsilon naught, which is this constant spinner. And then I will use delta and delta bar So delta gives me this term, and delta bar gives me that term. This unfortunately is written in the same confusing, unexplained way in all the papers on the subject. Anybody knows what I wrote there? Anybody recognize this? This is Young-Mills action, yes. So this is the supersymmetric Young-Mills. If you supersymmetrize it correctly on the sphere, so I told you again, Young-Mills, for example, is not conformal in 3 dimensions, so you need to specify how you're going to put it on S3. Of course, you're going to include this term, and you're going to include this term, and you're going to include this term. But then if you want to make it supersymmetric, you also include these terms. So this is equal to S Young-Mills. So this is rather peculiar that the localizing action that we're going to use, this delta V, is the Young-Mills action, and we're going to deform our action by an arbitrary multiple of the Young-Mills action. In particular, as I proved, the answer will not depend on the Young-Mills coupling constant. It will not, for a theory with the Young-Mills term and a theory without the Young-Mills term, if I can apply this, if it's supersymmetric, put on the sphere and so on, the Young-Mills term will not change the answer. So this is one of the interesting things about localization. We can calculate things exactly, but we can calculate it only in a restricted set, like on S3 or something like that. And the result will not depend on a lot of ingredients that go into the calculation. For example, whether we had to begin with a Young-Mills term or not, because we're anyhow, it will not depend on whether we include on the value of t, which is the Young-Mills coupling. Is this clear? So this is there are many more examples of these independencies of the localizing results of the S3 partition function. So the S3 partition function is completely irrespective of whether we take a theory with Young-Mills, Chern-Simons plus Young-Mills, or Chern-Simons without Young-Mills. Look at this segment. Okay, so where are we? We chose V, it was fermionic. Delta V is bosonic. And all of this goes through. Let's assume that there are no issues with infinity in the path integral and so on. So delta, so the partition function does not depend, as I said, on your Young-Mills term. You can include it or not include it. And you can include it with an infinite t. And so the solution will be dominated by delta V equal to 0. And we actually can restrict to the bosonic part because we don't expect a contribution from fermionic classical to the fermionic solutions. So the bosonic terms are just these 3 terms in the first row, and luckily they are each of them square. Actually, but to get this, you needed to integrate by parts to get this expression. So anyhow, you have a sum of 3 squares, so this delta V equals 0 implies f mu is equal to 0, d mu of sigma is equal to 0, and d plus sigma over r is equal to 0. So this is the space of solutions that we need to integrate over, the solutions to this equation. So we need flat connections on S3. There are none. So A is equal to 0. Sigma is equal to a constant, which we will call sigma naught. and D is equal to minus sigma naught over R. So sigma, which was originally, so the gauge field is turned off. Sigma, which was a field on S3, will now just be a constant, and D will be proportional to the same constant. So in this way, the path integral over A, sigma, lambda, and so on is reduced to this finite dimensional integral over the matrices sigma naught. Yes?
Are you assuming anything about the fields being smooth everywhere and things like this? That you have point-like weird things happening in S3?
No, so in quantum field theory we cannot assume that the fields are smooth. But in this case I cannot have funny things happening at a point. And S4, in the case of S4, four-dimensional theories on S4 and two-dimensional theories on S2, you can get funny things happening at a point. So you know that you cannot comb in S2, right? You can comb in S3, which is why I had here a bosonic symmetry which had no fixed points. But on S4, you're going to have fixed points. You're going to have a north and south pole, and there you're going to have this thing vanish, and you can find extra solutions, singular solutions to these equations. Here there are no singular solutions. I'm assuming here that, so this is when I'm considering the usual partition function. Actually, in one of my papers, it was listed up there, we considered an expectation value of something we call a vortex loop. A vortex loop is described by having a particular singularity along a curve along the psi direction. And then you violate your conditions. You don't require that the fields, that your modes are all normalizable and so on. You have actually this a very extreme singularity at this point. You have non-trivial holonomy around it. So the fields are not smooth, but they need to be normalizable. And in this case, you violate some of the conditions on the, you change the quantity, instead of the fields being, so the condition that you violate there is that an infinitesimal Wilson loop around any small vanishing curve will tend to zero as you shrink the curve. That is a condition, a normal condition you impose on the gauge field. In that case, you violate it and you require a particular value for the holonomy around this curve. So anything linked to this curve, infinitesimal curve linked to this particular psi curve, will have this holonomy, and then you change the quantization conditions. And you need to worry about this again. Again, it will be a finite space and so on, but in the normal case, this is not. Okay, so this is the space of solutions we want to integrate around. We want to integrate, but we need a. So what I said here only is that the path integral will be dominated by these configurations, but let's be a little bit careful about what that means. So let me expand all the fields around this point. So I'll define sigma equals to sigma naught plus 1 over square root of t sigma prime. D is equal minus sigma naught over r plus 1 over square root of t d prime. A will be replaced with 1 over square root of t a, and the same with lambda, and the same with the ghost c. So actually everywhere that I wrote it because it's a gauge theory. We need to do gauge fixing, and this delta should include, in addition to supersymmetry, also gauge transformations. So I need to put in a gauge fixing term and so on. But to simplify things, I will ignore it. It doesn't, at the end, things work out. And now we need to look at what happens to our action. So, the Super-Yang-Mills Lagrangian, we chose this space such that it will vanish on these fields. So these terms will vanish. It's a classical, there are terms which, so we need to worry about these terms and this term. So what we will find, the f mu nu term, for example, if we have in it the a to the fourth term, that will come with 1 over t squared. But the terms that are proportional, there are not going to be any terms proportional. So it's 0 times t to the 0 plus 0 times t to the minus a half. Check that. Plus 1 over t. And now everything that is quadratic in these fields. So we're going to have trace of minus a mu box a mu minus a mu commutator sigma naught squared. So the derivative here of sigma, the regular derivative part will give me 0, but the a mu comma sigma will be proportional to 1 over t of sigma naught. If I take here the fluctuation of sigma, it will be again smaller order, except for the d mu sigma prime, sorry, d mu sigma prime. And then there's going to be plus d plus sigma prime squared plus fermions. Plus order of t to the minus 3/2. But now, when I consider my theory, what I should include is in my calculation, is it? I need to include e to the minus the original action minus t times the localizing action. So I need to calculate S super Chern-Simons, for example, plus t S super Yang-Mills. And the super Chern-Simons action is not multiplied by t. So I need to take, in this decomposition of the fields, I'm scaling it like 1 over square root of t. So all terms proportional to a are going to vanish when I take t to infinity. But these terms will contribute. So all I have is minus integral d3x. And then I get this term here. Trace 2 d naught sigma naught, which is equal to minus sigma naught over r. And I get this term, the 1 over t term here gets multiplied by t here. So I get plus S superimmense quadratic. The interactions of superimmens, they're going to be here, and the lower, higher negative powers of t, so they will not appear in this approximation. So I have here plus or 2 minus a half, and this I can ignore when t goes to infinity. So the answer is that when I do the calculation, I'm going to have sigma naught appearing here. This expression for sigma naught. All the fluctuating terms in the fields, sigma prime, d prime, a, lambda, lambda bar, and the ghost, they will appear in my action, but only a quadratic action. So it's not that I don't have to do the path integral. I do have to do the full path integral over all these fields, but my action is quadratic. So I actually can do the full path integral. In this way, at the end I reduce it to a finite dimensional integral because I will do separately now the Gaussian integration over these modes, sigma prime, d prime, a, and lambda, and so on. And then we are going to be left with the integral over sigma, which will be the matrix model, which I'll solve tomorrow. Any questions? So, first thing you can do is you can diagonalize sigma naught, and this will introduce a von der Monte determinant. This usually is what you have when you diagonalize a matrix. The Jacobian is a van der Monte. So you can write it as a product I guess j sigma naught I sigma naught j squared, where a sigma naught I up to sigma naught I are the eigenvalues. If you consider a general group, not necessarily UN, then instead you have the product over all the positive roots of alpha. So if you don't know what this is, what a root system is for the algebra, anytime when I write this, you should think of it as that. Who knows what positive roots are? Who doesn't know what positive roots are? Who doesn't care? Okay, we're going to not use roots. Forget about it. You can continue not to care. You should have studied it at some point. So, there is a way to write all these. So, the problem arises here, so you should separate your fields. You have your commutator. So A, some of the components of A will be multiply, so you're going to have A as a matrix, so you're going to have Aij A times sigma I minus sigma J squared Aj I, something like that. So this off-diagonal components of A, these differences in the values of sigma will serve as a mass for them. Now the diagonal components, they will not get this. Likewise, sigma does not have, so there is just a mass term, but so there is d second derivative of sigma plus 2 or something like that times sigma squared. Right? So this is something like, there isn't. So this is something like minus sigma lox sigma, sigma prime. Actually, this T integral, you can just do it because it's a Gaussian. It's independent of sigma. And then you have this integration over sigma prime, which is also independent of sigma naught. So let me ignore all, I will ignore anything that is independent of sigma naught. So at the end, so whatever doesn't depend on sigma naught will give me some number, which does not depend on anything much. You can in particular then match it with a perturbative calculation that you do at recoupling. If it does not depend on sigma naught and on k, then I can ignore it and calculate it at recoupling in perturbation theory and match it. If you want, you can actually also do it exactly. But anyhow, we're going to find all kinds of infinities arising from calculating determinants and so on. So there are going to be all kinds of indeterminate things. So if you don't trust zeta function regularization or stuff like that, you will anyhow want to match with perturbation theory or something else that you trust. So all we need to worry about are these terms. So what we need to calculate is a integral j e to the minus plus aij x plus sigma naught I minus sigma naught j aj prime. So we need to do this, which is a Gaussian integral. So what we need to calculate, this will give us, then there is a fermionic term. There is another fermionic term, which is essentially lambda times b minus sigma lambda, something like that. So this will be equal to the determinant of b minus sigma divided by square root of det box squared schematically. This is sort of obvious. Sort of obvious. Nobody cares. Okay. So we need to calculate the determinant. So let's look at this determinant. So we need to calculate, we have a vector field. We need to do the spectral analysis of a vector. Right, this is an A mu. We need to do the spectral analysis of a vector on S3. So we need to solve a box minus n squared a mu minus lambda a mu. Solve for all these eigenvalues I, and that phi lambda I. So we need to find all the eigenvalues of this differential operator.
Now we have all possible polarizations of the vector field, but in the initial case we had only few of them.
We had only few of them.
We had the gauge invariance initially.
Yes.
But now we have simply the collection of scalar fields.
That's right. So, okay, no, so these are not scalar fields. These are vectors, but as I said, one should treat it correctly, introduce ghosts, take care of the gauge invariance, and then you have an arbitrary vector.
But the ghost determinants are sigma independent, so we can drop them.
That's right. Yes. So yes. So this also. So it will be so the indeed the ghost determinant is sigma independent, and we drop it. And here we have the determinant over regular all possible vectors that satisfy the gauge condition, because we'll add a gauge fixing term. So we will add so it will be all these vectors. Yes. Yes. So at this, so it, yeah. So here it will. So here you see I didn't put the ij indices, so I will need to take later a product over all I and j in this determinant. Okay. So spectral analysis on S3. Everybody knows the symmetry of S3? Yes, there is an SU2. What more? Give me more? More than one SU2? What do I have? Who has two SU2s? Anybody? Two SU2s, that's what we have. So, as we already know, we don't know any group theory except.
Don't we have all of them for?
Do you care about that?
Does it change anything? Does it change anything? Do you care about that?
I don't know. I don't care about that. No, it actually, well, I mean, we're immediately going to move to the Lie algebra, so it doesn't matter for what I'm going to say, but as you see, we're not the only one here who doesn't know group theory, and but luckily we all know SU2, right? Anybody doesn't know the representations of SU2? I guess the answer is yes. Okay, you want pretension or representations of SU2. So let me do the case of the scalar. So if instead of a mu we had a scalar, and we will actually have a scalar because we can couple this theory to chiral fields which have scalars, fine. Then we will get a similar equation but for scalars, and the harmonic analysis of scalars is slightly easier than the harmonic analysis of vectors. So what are the representations? So if I had a harmonic analysis on S2, what is the symmetry of S2? SO3. SO3 is SU2, more or less, right? If I had a scalar on S2, what are the allowed modes? How do you label them? L and M, yes. I'll call it J and M. Okay? So if we have two SU2s, we have J1 M1 and J2 M2. So that is if we have a general representation of SU2 cross SU2. But if it's a scalar, we have that J1 is equal to J2 for a scalar. And we have that box minus box is equal to 1 over 4 over r squared times two j plus 1 squared. So that is different from on S2. What is it instead on S2? J times j plus 1, yes. And the multiplicity?
2j plus 1.
2j plus 1 in SU2 and for S2. For S3? 2j plus 1 squared. And something here is wrong. This is not the answer. So here it's 4. It is like on S2. Sorry, just with this 4 here. It is like on S2. J times j plus 1, but times 4. And the multiplicity, because m is greater or equal minus j, so equal to j, you have here m1 and m2 each in this range. That's why you get this square. The vector, in that case you have j1 equals j2 plus minus 1. And from this you can immediately calculate what is the multiplicity, because in most of the multiplicity I told you how to calculate. You have two polarization modes which correspond to this plus and minus. You need to calculate the Laplacian. In that case, box is equal to minus 1 over r squared 2j plus 1 squared, and the multiplicity is equal to 4j times 2j plus 1. This you can immediately calculate. From this you need a little bit more group theory to work out. Okay, so again, this I didn't do in full detail. You can, if you want it in the goriest detail, you can look at the appendix of my paper with Drukker and Passerini. We have all the explicit spherical harmonics with some nasty generalization. If you want slicker proofs of these expressions, you can find them in the Molino review, for example. So what we find is that the determinant for the boson, well, let me write the full determinant. Is equal to product over I and j. So now I'm introducing this I and j again. I different from j. I have product n equals 1 to infinity, where n is equal to 2j in this notation, because j can be half integer. So usually when you're on S2 and you have a scalar, then j would be an integer, but because here you have two of them, actually a half integer j is still good for a scalar. And here also, as long as the difference is 1. So if the difference between them is an integer, they're bosons. If the difference is half integer, they're fermions. That is slightly different. That's the quantization condition on S3 instead of S2. So we have the product over these quantities. So I will throw out the 1 over r terms, which are not important. Or I will set r to 1, or I will rescale sigma by r. Any way you want to do it, this is not important. And what I have there is n plus 1 squared. That was a scalar, so this is this. This is n plus 1 squared plus sigma naught I minus sigma naught j squared. And I have a bunch of them. I have a 2n times n plus 2. That's 2n times n plus 2. That's the multiplicity of this eigenvalue. And then the fermions I didn't do for you, but I can tell you what it is. It's n plus I sigma I minus sigma j times minus n minus 1 plus I sigma I minus sigma j, and all this to the power n times n plus 1. Okay, is this roughly clear how I got this expression? More than roughly or less than roughly?
What happened to the r squared?
I set r to 1, or I rescaled r into sigma, and I ignore an infinite product of 1 over r. Right? But you can keep it. You can keep it. You can keep it. But you can set r to 1, or you can. It will also cancel between numerator and denominator. But then you need to rescale sigma by r. So sigma has dimensions, 1. So I rescaled it, so it now doesn't have dimensions. Or I set the radius to 1. So this is equal to the product, and it's not equal to j, product n equals 1 to infinity. And now I have this n plus I sigma I minus sigma j to the n times n plus 1. I have n plus 1 minus I sigma I minus sigma j. N times n plus 1. Now I can shift this actually to be here n plus 1 at the expense of making this n times n minus 1. And of course you should be worried about what happens at the beginning of the thing. I will not. Somebody was once. That's good enough. And downstairs you have n plus 1 plus I sigma naught, sigma I minus sigma j, sigma naught I minus sigma j. To the product, to the power. Sorry. After I took this was divided by 2 because I needed a square root. Take the square root. The degeneracy. So I have n times n. Plus 1, sorry. This is n plus 1 and this is n plus 1. That's n plus 2. Yeah. This is n times n plus 2 and this is n plus 1 minus n sigma I minus sigma j times n plus 2. And now I have similar terms appearing in the numerator and the denominator, and I just need to worry about the multiplicity. So here I have n plus 1 times n plus 2, here I have n times n plus 2. So I can cancel this, I can cancel this, just n plus 2. And here I have a n times n plus 1 and so on, so I have just n. The denominator. This is not exactly what I wanted. Oh, this is what I wanted. So I can also write it again, shifting it to n. This is equal product different from j. Product n equals 1 to infinity. N plus I sigma I minus sigma j to the n plus 1 divided by n minus I sigma I minus sigma j n minus 1. And now I can take instead the product over I less than j, and then I get at the denominator and the numerator both plus and minus. So all I get would be, so everything here would be doubled with a minus sign, and then divided by this, I will just get n plus I sigma minus sigma squared, and minus I sigma minus sigma squared. So this is equal, there's also a product over n. I have the product over I less than j, product n equals 1 to infinity n squared plus sigma naught I minus sigma naught j squared, all this squared. Anybody knows what this product is?
Okay, parabolic sine divided by parabolic sine of
That was too
e
quick.
sigma minus sigma divided by b.
Yes. So this is equal to a product n equals 1 to infinity. So let me look at fixed or fixed I and j. I have here n to the fourth times a product n equals 1 to infinity 1 plus I sigma minus sigma over n 1 minus I sigma minus sigma over n. Let me ignore this infinite thing, which does not depend on sigma anyhow. I told you I ignore all of those. This is equal to the product over all n's of 1 plus I sigma I minus sigma j over n divided by the case no, sorry. I'm doing this wrong. I should have done this like this. Anyhow, the question is, what is a function that that vanishes whenever sigma minus sigma prime is an imaginary integer, except for 0. So if it vanishes at all imaginary integers, this is a cosh or a cinch. It's a cinch in this case. But because I don't include here 0, it doesn't vanish when sigma is 0. It's just 1 times 1 infinite number of times. This is equal to cinch I sigma I minus sigma j divided by the I sigma I minus sigma j. So I didn't miss the square because I'm missing the square. Yes, I'm missing the square. X. So you can see that it has the right zeros. It has the right value at when the argument is 0. And so it's the same function. Doesn't have any more poles of zeros. So this is the function. And then you need to multiply all I and j, and you need to multiply it by this Vandermonde, which is here, which cancels this denominator term. So we get that the partition function right here. Z is equal to e to the minus 2 trace sigma naught squared. I ignore r. Volume S3. And what I forgot here was the I came with this whole time. And this is multiplied by product I less than j sin squared I sigma worried about factor of pi, and this is integral over sigma I. So this is what we get from the localization. We reduced the full path integral into this finite dimensional matrix integral over n variables. Now, what I'm going to do in my last minus 10 minutes is mention what happens if we have other fields in the theory. And so this was just if we have vector multiplets, we have this Chern-Simons term. As I told you, if we have a vector, if we have a Young-Mills term, it doesn't matter at all. We'll just get more. So this is not in the exponent, right? This appears outside of the exponent. This is just a measure of integration. It will just be this without the exponent. Just a van der Waals-like determinant. But we can include matter fields, phi, f, and so on. And then you need to follow a similar procedure for them. In that case, miraculously again, you find that with the same delta, you can take a delta v to be equal to s chiral. So the same way that I got the Young-Mills action as the localizing action, I can get the chiral action as the localizing action. And this tells you that there will not be, and in that case you find that a delta v equals 0 implies that phi is equal to 0. So you have no more modes to integrate over. You don't need to, no more constant modes, phi, like you had here, sigma naught. So all you need to do is to do the full path integral over these modes is to calculate the determinant for the quadratic chiral action. So you have again a similar spectral analysis now involving fermions and scalars. So you're going to get again some kind of ratio like here. And then it depends on whether you take the dimension to be 1/2 or not. The answer will depend on that. And it will depend on the representation of your matter. Because it can be in the fundamental representation of the group, it can be in bifundamental, it can be charged under two different gauge groups, and so on. In the simple case that will be applicable for us, if so you're going to have that fermion that v minus sigma. Sigma will appear in the action divided by square root that box minus sigma. In the case that will be relevant for us, if you take this mod square, which means you have a matter charged under conjugate representations for so this is for fundamental plus anti-fundamental. The result will be 1 over cosh sigma, where the appropriate charges So we have sinh in the denominator from the vectors and the matter fields. If we take the correct combination of matter fields, we get cosh. There is no result or other fields. It's a double sign function instead of the cosh. But for the discussion tomorrow of ATJM, this is what we will need. So I'll conclude now, and tomorrow we reduced the full path integral to a matrix model, and tomorrow I will explain how to solve this matrix model. So this will be our starting point, and we're going to introduce a whole new set of techniques.